right, so we've been taking a look at instantaneous power, and we've defined real power as well as reactive power. We took a look at the power for purely resistive loads, and we determined that there is real power that's being delivered to the load. We took a look at the power for a purely inductive load, and we determined that there's no actual real power that's actually being delivered to the inductive load. We have one last type of load to take a look at, and that is the capacitive one. So let's take a look at power for purely capacitive circuits or loads. So suppose that we had a capacitor here, characterized by a capacitance C. One of the things that we can do is we can place a sinusoidal voltage across it, in which case there will be a sinusoidal current that flows through the terminals. We know that the IV characteristics for a capacitor are such that the current in the capacitor is equal to the capacitance times the time rate of change of the voltage. And just like what we did for the inductor, where we could actually draw some conclusions on the phase constant for the voltage compared to the current, we can do a similar thing for the capacitor. So since this is a sinusoidal circuit, the voltage is going to be the magnitude of the voltage times the cosine of omega t plus its phase constant. Similarly, for the current, it's going to be its magnitude times the cosine omega t plus its own particular constant. And just like before, we can take these and we can put them into the IV characteristics. Now, on the left-hand side of that equation, I have the current, while on the right-hand side of the equation, I do actually have to take the time derivative of v sub m times cosine of omega t plus theta sub v, like this. And we know, based on our previous calculations, that the time derivative of cosine omega t is going to give us negative sign. And by the chain rule, we're also going to pull out a negative omega term. So this is minus omega c v sub m times the sine of omega t plus theta v. Using the same identity that we used last time, so the trig identity that we can call upon is that the sine of any angle is equal to the cosine of the angle plus 90 degrees. Notice that this directly applies to this sinusoid, even with a minus sign. So this whole equation can be rewritten with the absorption of the minus sign as omega c v sub m times the cosine of omega t plus theta v plus 90 degrees. Now, since we actually have constant times cosine of an argument, the arguments of each cosine must be the same. The magnitudes must also be the same. So this must be the same as that. And more importantly, these two internally must be equal for a capacitor, which leads us to conclude that theta I is equal to theta v plus 90 degrees. This also means that since theta I is equal to theta v plus 90, that unlike an inductive load where the current was lagging behind the voltage, in this particular case the current, in terms of the nomenclature of electrical engineering, here the current doesn't lag, but it leads the voltage. This terminology is going to be used over and over and over whenever we're dealing with power systems. Right? On top of that, notice that theta v minus theta I, unlike in a capacitive circuit where it's positive 90 degrees, this one is negative 90 degrees. So this one is very important. Let's box this in red. This one itself is important too. Let's box this in green. And let's go back to the context once again of our instantaneous power. So our instantaneous power in general was the real power plus the real power times the cosine of 2 omega t minus the reactive power times the sine of 2 omega t, where the real power was v sub m times v sub I times the cosine of theta v minus theta I, and the reactive power was v sub m I sub m over 2 times the sine of theta v minus theta I. Notice that this in here and this in here, well, they're both minus 90 degrees. Right. Now, for the cosine of minus 90 degrees, this turns into 0, and this right here actually turns into minus 1. So this is 0. This is minus v sub m I sub m over 2, right? Which means that the power for a purely capacitive load, right, is of the form minus q times the sine of 2 omega t, where the first two terms have completely dropped out. P is equal to 0 because P is equal to 0. Right? On top of that, even though this term right here might not actually be equal to 0, so at any given time the instantaneous power itself might be positive, it might be negative, the average power for a purely capacitive load, because of the presence of the sinusoid, right? So here, over one period, well, this sinusoid is always going to end up disappearing. Once again, showing, as we did for purely inductive loads, that capacitors themselves, right, they can store energy and release it to the circuit later on, but they can never actually dissipate energy. They can never do real work or deliver real power, which is something that's extremely important when it comes to these types of circuits.